All right, here we're going to take a look at rationalizing imaginary denominators. All right, so to rationalize the imaginary denominators, this would be division of complex numbers. So we've looked at addition and subtraction. Well, they're kind of the same thing. We looked at multiplication. Now here we're taking a look at the division of complex numbers, and it's called rationalizing imaginary denominators, or rationalize imaginary denominators. What it means to rationalize is to take a number that is not rational and turn it into a number that is rational. And by that, imaginary numbers are not rational numbers, they're complex. Right? So if you go back and think about this, right, our real number system, our rational numbers look like fractions, right? And if we're going to rationalize a denominator, we don't necessarily want a fraction in the denominator. Our end goal really is going to make it a natural number, right? So we're going to get real specific. Instead of saying naturalize imagine, we just call it rationalizing. Turn it into a rational number. So since natural numbers are definitely in the family of rationals, this is an okay thing to do. So, the division of complex numbers. I'm going to go through the steps on how to do this, and then we're going to do a couple of examples. So, the process, step one, we're going to multiply the that's an M, numerator and denominator by the complex conjugate of the denominator. And step two is we're going to simplify. Really, I could have just been a one-step deal. Oh, man. I cracked myself up. Woo. Okay. So let's take a look at what does this really look like? What does this mean? Multiply the numerator and the denominator by the complex conjugate of the denominator. What does that really mean? Let's just take a random number. So, okay, nice. Pick a number for us. We have 2, and then we'll say plus 4i divided by 1. Let's go minus 4i. Okay. So here we have 2 plus 4i over 1 minus 4i. So if you're trying to figure out what in the world a complex conjugate is, I got a video for that. You should have watched it already. So I'm going to multiply the numerator and the denominator by that. So here I'm going to multiply both the numerator and the denominator by the complex conjugate of the denominator. So it's going to be 1 plus 4i over 1 plus 4i. Okay? When I multiply a number by 1, right? This is just 1. If I multiply a number by 1, I'm not changing the value. I'm just changing the way it looks. I'm not changing the value of this number. I'm just changing the way it looks. So I'm going to multiply across the top, multiply across the bottom, and then I'm going to simplify. So here we go. 2 times 1 is 2. I'm going to go ahead and put my denominator there, or my fraction there. So 2 times 1 is 2. 2 times 4i gives me an 8i. 4i times 1 is a positive 4i. And 4i times 4i is a positive 16i squared. Now we're going to multiply the denominators, right? So 1 times 1 is 1. 1 times 4i is a positive 4i. Negative 4i times 1 is a negative 4i. A negative 4i times a positive 4i is a negative 16i squared. All right, so this is where I'm going to clean it up. I'm going to take 2 steps with my numerator, 2 steps with my denominator. Combine my like terms and switch I squared to -1. So I'm not messing with that 2. 8i plus 4i is a positive 12i plus 16 times -1. On the bottom, I have 1. I didn't mess with that 1. 4i minus 4i is 0, so I don't need him. Minus 16 times -1. And now I'm just going to multiply my 16 on the top by -1 and the -16 on the bottom by -1. So I get 2 plus 12i minus 16 over 1 plus 16. And now I'm going to combine my like terms. 2 and -16 is a -14 plus 12i on top. 1 plus 16 is 17. And now, here, I have the same number as before, but instead of an imaginary number on the denominator, it is now a rational number. 17 is considered to be rational. So, instead of a complex number in the denominator or an imaginary number in the denominator, I now have a rational number in the denominator. Let's do a couple of examples that you're going to see in the homework here. 6 over -4i. Ooh. What is the complex conjugate for -4i? It's like saying 0 minus 4i, right? At 0 minus 4i, so the complex conjugate for 0 minus 4i would just be a positive 4i. So I'm multiplying the numerator and the denominator by the complex conjugate of the denominator. Even though it's just the imaginary part, the complex conjugate switches that sign. So instead of 0 minus 4i, it's going to be 0 plus 4i, but I don't need the 0. And now multiply across top, cross bottom. 6 times 4i is 24i. -4i times a positive 4i is a -16i squared. I squared is really -1, so here I get 24i over -16 times a -1. So that gives me 24i over a positive 16. Now we can reduce. What do 24 and 16 both have in common? They both have a 2. We can go a little bit bigger than 2. They both have a 4. But I think we can go bigger than that, right? What about 8? Yeah, 24 divided by 8 is 3. 16 divided by 8 is 2. So I get 3i over 2. All right. Let's take a look at this other example over here. -3 plus 10i over -6i. The complex conjugate for -6i, as we saw over here, would then be a positive 6i. And now here I have what's considered a binomial times a monomial. So here on my numerator, I have to distribute. So -6i, or excuse me, positive 6i times a -3 would be -18i. 6i times 10i is a positive 60i squared. The denominator then, -6i times a positive 6i is a -36i squared. Now I'm just going to simplify by taking my I squareds and turning them into -1. So I have -18i plus 60 times -1 over -36 times -1. And I can simplify this now. I'm going to multiply. I have a positive 60 times -1, and I want this in a plus bi form. So I want my real part first. So I end up with -60 minus 18i. A -36 times a -1 is a positive 36. Look what I did there. I switch the imaginary and the real part so that the real part's first, right? Complex numbers are in the form of a plus bi. And now all of these seemingly can reduce by 6. So if I reduce everybody here by 6, I get negative 10 minus 3i over 6. That is my final answer. So make sure you reduce as much as you possibly can with these. All right, let's take a look at the last two examples. Here I have 1 over negative 8 minus 5i. So we want to multiply this by the complex conjugate of the denominator. The complex conjugate of the denominator is going to be negative 8 plus 5i. So negative 8 plus 5i, negative 8 plus 5i. And it's nice with a 1 on top. 1 times anything is itself. So then I get negative 8 plus 5i for the top. And now on the bottom, we're going to have to FOIL, right? So negative 8 times a negative 8 is a positive 64. Negative 8 times a positive 5i, negative 40i. A negative 5i times a negative 8 is a positive 40i. And negative 5i times a positive 5i is a negative 25i squared. Now I want to combine my like terms. And switch I squared to negative 1. So the numerator stays the same, negative 8 plus 5i over. And then I'd have 64, that's 0, minus 25 times negative 1. And that can be simplified. So I get negative 8 plus 5i over 64 plus 25. And now combining my like terms, 64 plus 25 is 89. So I get negative 8 plus 5i over 89. Ask myself, do 8, 5, and 89 all reduce by the same number? I could easily say no, because 8 and 5 don't reduce by the same number. So that is my final answer. All right, let's do this last one here. We have negative 3 minus 7i over 7 plus 10i. Little pen mark there. That's why I hate mathing in pen, but pencil just doesn't show up on these. So 7 plus 10i, my conjugate's going to be 7 minus 10i. So it's 7 minus 10i on both the top and the bottom. And now this is going to be a lot like the first example that we did, where we have to FOIL the top and FOIL the bottom. So negative 3 times 7 is a negative 21. I'm going to go ahead and put my fraction there. Negative 3 times a negative 10i is a positive 30i. Negative 7i times a positive 7i is a negative 49i. A negative 7i times a negative 10i is a positive 70i squared. And now for the denominator, right, I'm going to multiply 7 plus 10i and 7 minus 10i. So 7 times 7 is 49. 7 times negative 10i is a negative 70i. 10i times 7 is a positive 70i. 10i and a negative 10i is a negative 100i squared. And then remember, I got 2 steps here. I want to combine my like terms in the middle and switch my I squareds to negative 1. So I get negative 21, a negative 30, and a positive 30, positive 30 and negative 49 is a negative 19i, plus 70 times negative 1, all over. 49 stays. Negative 70, positive 70, that goes to 0. It's by design. It's why we do this. Minus 100 times negative 1. And now I'm going to multiply these guys by negative 1. I get negative 21 minus 19i minus 70 over 49 plus 100. And clean it up. Negative 21, a negative 70, you have a negative 91 minus 19i all over 149. 9. Now I got to ask myself, do 91, 19, and 149 reduce by the same number? In this instance, no, they do not. And we are done.